Well, I'm Cesar Cerrudo. First of all, thank you for Hacking the Box, for the opportunity to be here sharing this with you. So let's start with the presentation. So what's LoRaWAN? So LoRaWAN means long range wide area network. And it's an IoT protocol that is built on top of the LoRa protocol. The LoRa protocol is at the physical layer, the radio frequency part, because it's a wireless protocol. And then LoRaWAN, as we are going to see, is at the MAC layer of the stack, right? So it's a low power, so it has a very low energy consumption. Has a long range, so it's very easy to create the infrastructure for LoRaWAN. You just put an antenna, a gateway, and you can cover several kilometers. There have been records in Europe where people put the devices in a balloon and they just let the balloon go, and they have been able to transmit up to 700 kilometers. This is not working well. So it works on a free radio frequency spectrum, so anyone can operate a LoRaWAN network. Then it's a very robust protocol, so it has very low interference, so you can really rely on the transmissions. And of course, you can have everything, so it's a very low bandwidth, so the transmission is very few bits per second. So there you can see the stack. So you have LoRa protocol at the bottom, where is the physical layer. Then you have the MAC layer, where is the LoRaWAN protocol, and then you have the application level. That's a very simplified version of the stack of this. So this is how the infrastructure looks like. It's very simple. You have the end devices, the sensors, then you have the gateways, which are basically bridges that they take the information that goes over the air on LoRaWAN protocol, and then they translate it to IP, to the IP stack, and just forward the information. They're basically a bridge between the LoRaWAN and IP, TCP/IP. And then the network server is the one that will get the information from the gateway. They will parse the information from the LoRaWAN protocol, because basically the protocol is encapsulated over TCP/IP. The information is get by the network server, so it parses the information and will forward it to the application layer, so it can be used by any application, the information that you get from the devices. So it's very simple. You have the end devices, the gateway getting the information, forwarding it to the network servers, and then the network server sending the information to the application servers. I'm not sure why it's not working well. So you have an idea of how popular is LoRaWAN. Right now, there are more than 100 network operators giving LoRaWAN coverage around the world. So a big telco provider, for instance, on France, you have Orange that is covering all of France, providing LoRaWAN infrastructure. And the same on other European countries, even on Asia. In the US, you have Comcast with Machine Q providing also infrastructure services for LoRaWAN. It grew 100% last year, and this year keeps growing. To give you an example, for instance, on Brazil, the American Tower company, they deployed 400,000 devices, and this year they plan to deploy a lot more. And then in France, Boila, or Veolia, I'm not sure how it's pronounced, they are doing some testing, and they are intending to deploy 3 million smart meters. I think it was for water consumption. So as you can see, is a protocol that is getting very popular, mostly related with the concept of smart cities in order to, implement services and very cheap to, in this case was for smart metering. So there is a LoRa Alliance, which is a group of companies that is backed by Semtech. Semtech is the creator of the LoRa technology. So they created this alliance where many big technology companies are members, so they are promoting the adoption of LoRaWAN. And this alliance is growing every year, and you can see there that are the main technology companies from around the world. It has a great developer ecosystem where people is constantly learning to use LoRaWAN, developing some tools, products, and it's growing also every day. And they say, this is based on information mostly for the LoRa Alliance, right? This is official information. They say that right now there are 80 million devices worldwide and more than 10,000 networks. So some projection from market researchers, they say by 2021 there will be 100 million new devices every year if everything continues to grow as today, as a projection, right? And then the amount being spent by companies, different kind of companies using LoRaWAN technology will be around $1.3 billion for connectivity for 2023. So you can see there is a huge market, a lot of potential, and everything indicates that it will just keep growing. And that's some of the companies that are members of the LoRa Alliance, and you can see how it is growing over the year. So in 2015, there was just starting IBM and Semtech, one of the few companies starting with this, and right now you have more than 300 companies that are part of the LoRa Alliance. So they are pushing really hard for this technology and trying to get implemented worldwide. That's it.
So now I'm going to explain a little bit about the security features of LoRaWAN. I want to recall here that it's going to be about the LoRaWAN in its version 1.03. There's nowadays a newer version, but that I'll explain later in one of the last slides. So for starting, one of the security features that LoRaWAN provides are counters for messages, for both messages that goes from devices to the server, and which is the uplink traffic, and messages that come from the server to the devices. These counters are of 16 bits, so these counters go from 0 to approximately 65,000. And once they reach its highest limit, its highest value, they go back to 0. They are reset to 0. Another feature which is optional are the possibility to confirm the messages sent from the devices to the network server. The third feature, and this is very important, is the integrity control that it provides. And this integrity control is achieved by using the network session key, and this is only between the end devices and the network server. And please note that there is a line in red with a question mark, and that's to note that there is no, or LoRaWAN doesn't define integrity between the network server and the application of the user applications. And we'll see that that's like that's seen as or that derives in a vulnerability later. Another cool feature, very important, is the possibility or the feature to encrypt the messages between end devices and the applications, and this is end-to-end encryption, and this is achieved by the application session key. So the way these two application session keys are generated or retrieved, it's based on the activation method that was chosen for each device. LoRaWAN offers like two activation methods. One of these is the ABP, which stands for activation by personalization, and the other one is over-the-air activation. So I'm going to explain a little bit about this kind of activations. So the first one is the ABP, which is the more simple. It only requires that session keys are hard-coded into the devices and in the network server, of course. So it has like a kind of couple of bad implications in security, because we'll later see that to have the session keys or to reuse the same session keys, it implies to use the same cryptography for achieving the integrity and encryption, and we'll see that that's not a good practice, and it's not recommended for production environments. On the other hand, we have the over-the-air activation, where the session keys here are generated like dynamically, and this is achieved by a procedure which is called the join procedure, which we can see as a kind of handshake between the end device and the network server. Here, the session keys are generated starting with a root key, which is called the app key. And this key is the one that's hard-coded in the device and in the network server, of course. So this join procedure is always started by the device, which sends a join request message where it travels many data, but the most important for here are two. First is the device identifier, and the other one is the dev nonce. The dev nonce, for those who don't know what's a nonce, it means number used once. So this nonce is used for avoiding replay attacks of the join request messages. And this data is signed with the app key. We'll later see how the signing is done. So when the network server receives this message, it first of all, it checks that the device is properly part of the LoRa network it wants to join, and then it replies with a join accept message to the device. And so this join accept message also has like many data, but the most important here are three. First, the first one is the device address, which is an identifier that lasts the same, it lasts the same as the session keys. It's like a session identifier. The other data is an app nonce, which is the same as the dev nonce, but here it's generated by the network server, and that's for the same purpose to avoid replay attacks. And the last one is a network identifier, which is an identifier that all the devices across the network share. And this data is encrypted using the app key. So if we want to sniff, for example, join accept, we'll only see the header that says the join accept, and then we'll see like a big chunk of encrypted bytes. So once these messages are exchanged, now both elements can derive the session keys, and once they have the session keys, they can start to exchange data messages between each other. So now I'm going to explain how the integrity and the confidentiality is achieved in a high level. And this is also in LoRaWAN v version 103. So to achieve the integrity, all the messages are appended with a MIC, which stands for Message Integrity Code. And to compute the MIC, we have like two big steps. The first one is to calculate a hash doing AS128 in CMAC mode with the whole packet we want to sign, and the network session key, which, if you recall, it is a session key that its purpose is for integrity. So once we have this hash, we only take the first byte and we append it to the end of the message. On the other hand, the confidentiality, today I mentioned that we have like end-to-end confidentiality between the end devices and the user application. What I didn't mention is that only the data payload of the application is the one that's ciphered. So the rest of the LoRaWAN headers are sending plain text, but that's not a big issue. So like for computing also or doing encryption, we can see it as a two-step operation. The first one is to compute, let's say, an S block, which is the result of encrypting with the application session key. We encrypt like a fixed pool of bytes with the counter of the message that we are going to cipher. So once we compute that block, we have that block, we do an XOR operation with the data payload that we want to cipher. Please, I want you to recall this because in the next slide we'll see that it derives into a vulnerability. So you should recall that we have the S block that depends directly on the application session key and on the counter that we are going of the message that we are going to encrypt. And this S block is used to perform an XOR operation with the payload directly. So about the vulnerabilities, there is plenty of material on the internet that you can search about. There are like big 4 vulnerabilities, at least for this version. The previous version has more vulnerabilities even. So the first one is the replay attack. And this vulnerability is caused in situations where the end devices reach its higher counter and then its counter is reset to 0. And in that moment, session keys aren't regenerated because LoRaWAN doesn't specify that implementation should regenerate the session keys. So many of them just don't regenerate them. So this allows an attacker that could have captured, like previously, a lot of messages to replay a message, which will take like 2 effects on the network server. The first one is that the network server will be accepting like previous data, like old data, as if it were from generated like currently now. And the other effect is that it will cause a denial of service on the device. And this is because LoRaWAN specification, which says that network servers should only accept messages with a higher counter than the last counter that was received. So let's put it in practice. Let's suppose that we have a device, for example, whose last message was the number 10, and then we have an attacker with a captured message from the previous session, which is, is the same session because we have the same session keys. So an attacker that has a message captured, now with a counter number 100, let's suppose, and now the attacker replaced this message. So in this situation, the device would have to send like 90 more messages until the server restarts to accept these messages from the device. So there's another vulnerability also related to this problem that session keys aren't regenerated. If session keys aren't generated, it implies that we'll be using the same crypto. So there's another vulnerability related to the use of the same crypto, which is the eavesdropping, which allows an attacker that could have captured a bunch of messages and could have like a little bit of knowledge about the payload that is ciphered to start to get certain bits and then to be able to decrypt like the whole payload. The third vulnerability is the bit flipping, which, if you recall that today I showed that the red line, that LoRaWAN doesn't define integrity between the network server and the application server. So an attacker that could have access to that channel, between the network server and the application server, could flip certain bits, and which will be unnoticed by the end user at the decryption time. And of course, the user will get incorrect data, different from the one that was previously sent from the device. And the last vulnerability is the acknowledged messages spoofing, and this is because acknowledged messages don't specify which message they are confirming. They don't specify the counter of the message they are confirming. So an attacker that could have captured at least one acknowledged message could start to replay this message to the devices, so the devices would just keep on sending messages as if it were like normal, unless, or and for example, if there's no connection with the network server, the devices would just keep on sending messages. So this, what I previously mentioned, was LoRaWAN in its version 1.03. Nowadays we have this new version, which is 1.1, where most of the vulnerabilities that I mentioned later were pretty much mitigated. We can see that here in this new graphic we have a couple of more elements in the infrastructure, where the most important is the join server now, whose responsibility now is to generate the session keys instead of doing so the network server. Moreover, we have like, instead of one root key, instead of the app key, we have like 2 root keys now. And instead of having 2 session keys, we have 6 of them now. And there are other cool features more. So the security in this version of LoRaWAN was pretty much enhanced, but there is a big issue with, not with the protocol itself, but with the vendors. And that's the problem is that the vendors aren't still embracing this new version. For example, there are even still vendors that they're using the version 1.02, which has a lot of more vulnerabilities proven than the version that I was speaking about earlier. Sorry.
Honestly, one of the main problems with LoRaWAN security, which is that keys are everywhere. And by everywhere, I really mean it. As you heard from Martínez, you have the app key, which is the root key, and is the key for everything, because that key is used to generate the session key and also the application key. So we have the keys that should be put in the device. So they are usually put by the device manufacturer. So they will embed the keys on the firmware or any other chip in the device, and will ship the device to the person or to the company acquiring the devices. So that's one possible leak. The vendor knows the app key. Then how they transmit the key to the user, to the end user. They put the keys in a device level. So anyone with physical access to the device can read the keys from there. Like I said, they put the device in the firmware, on the memory of the devices. That means that also someone with access to the device can extract the key from the firmware, from the memory. Then when you are, deploying devices, someone has to configure them, someone has to install them. So for that, you have technicians that they will have to, configure everything so the devices can be part of the LoRa network. And this technician also have access to the app key. We also have found the keys that are available in open source code. So you look around in the internet, you will see that the keys sometimes are leaked there. As an example, sometimes distributed by the vendor, so you can implement your own firmware, your own features. Then for deployment, for configuration, like I said, the technicians use a mobile application most of the time. So the keys, once the device is configured, will remain in the mobile application too. That's another way to get the key. When the vendor ship devices, sometimes they will ship, in devices in the hundreds, in the thousands. So one way they used to share the keys also with the user is in an Excel sheet or in a text file. They will send all the keys there. They will send it by email. They will send it by, other communication channel, but they will share in a file. Then the network servers, and in the newest version, the join servers, they also have the keys because they have to create the session key from that, right? And then we even have found keys on forums where users are trying to program their devices or try to use the LoRaWAN network, and they will ask a question and they will mention the keys they are using on their devices. So you can see there is a lot of places where you can get the key. And this key is used for generating the most important keys. So if you get this key, then game is over. You can get the traffic and decrypt it. So there you can see some examples of the key in the, one is the label in a device, where the key is printed, and the other is a part of a mobile application where the key is configured or read from the device. So on top of that, then use it in production, you have many problems with weak keys. So people will use non-random key or really easy to get keys. For instance, they will put all ones in the key, they will put all zeros, or they will put 0, 1, 2, 3, 4, etc. And we can see this on production system because we have tested this and found this in the wild. Some vendors will ship keys that are hard-coded, that are fixed. You can't change them. They will provide documentation saying, okay, the keys on your device is this, and you have to use this key, and you can't change it. So it's very stupid, right? Because someone with access to the documentation or someone with access to the, like I said, text file or to the labels can find the key, then decrypt all the traffic, and you as a user are not able to change the key. Another common problem is that you have a deployment, I don't know, 100,000 devices, and they will use all the keys, the same key for all the devices. Which means that if someone compromises the key, then he will have access to the whole network. And then another problem is that the app key is created using some public available information that is transmitted in clear text by the protocol. For example, by the app UI or the dev UI, this information is sent over the air in clear text. In some deployment, people is using this information that is publicly available to generate the app key. So what are the main threats? Well, like I said at the beginning, this is a technology that provides long-range communication. So you can capture with the right equipment, which is not expensive. It could be an antenna that's worth, I don't know, $100, and a gateway, which is very, very, very cheap too. You can capture packets from miles away, kilometers away. And right now, you could even do it in the near future from the space, because there are current projects that are building nano-satellites, low-orbit satellites that are at 400, 600 kilometers in the orbit, and they can get LoRaWAN traffic. They will be like satellite gateways for LoRaWAN networks. So as you can see, you could be able to capture LoRaWAN traffic as an attacker for a really long way. So another threat is the offline key cracking. That means that you can capture LoRaWAN traffic, save it, and then based on all these problems with keys that I already mentioned, you can use a key cracking program, let it run in, and try to find keys for the network that you already captured the packets. Even like Matthias mentioned, in the new version, there is another key, but that key has the same problem. So you could also crack that newer key. Another threat is that the key stealing, because like I said, the key is available on the devices. So if in a real-life deployment, you could have a device that could be accessed by someone physically. He could steal the device, and then extract the key from the firmware, from the memory. By Bluetooth, how? Because sometimes some devices offer functionality, like I said, to configure by a mobile application, so you connect to the device by Bluetooth, and there you can configure the keys, etc. So if Bluetooth is not a very secure protocol, and sometimes you get default synchronization keys, so you could, as an attacker, use Bluetooth to extract the key from a device. Then, like I said, the manufacturer put the keys on the device. So as an attacker, if you hack the manufacturer, you could have access to thousands of keys. The same with the service provider. The service provider or that runs some part of the infrastructure, that runs the network servers or the joint servers in the newer protocol. So those servers have the keys from the whole network. So as an attacker, if you can compromise the server, then you can download all the keys. Another threat is that malicious data injection. Once you got the keys, then you can decrypt the messages, the packet, the traffic. That means that you can create your own messages, your own packets. So you could inject fake data in a LoRaWAN network. Yeah, another threat is related with denial of service attack, because once you get the keys, then you can desynchronize, for instance, the communication between the devices and the network servers. Like Matthias said, you can increase the counter of the messages, so the network server will ignore the real messages from the devices. There are other also denial of service attacks, because you can just play with the protocol at will, and then the devices or the network server won't be able to communicate with each other. And now we are also starting to research some possibilities with a newer version where we could create ransomware in the way that, because we get the keys, then we can change the session keys, and then the network won't work because the network infrastructure won't be able to communicate with the devices. So we are starting to research possible ransomware where we change the session keys, and then you, as an attacker, can ask to the infrastructure owner, okay, you want to communicate with your devices, then you have to pay to get the keys. But that's not, we are just starting, we just to mention as an idea mostly at this stage, because we haven't finished doing tests, but it is an interesting concept. So while we are doing this research, when we started, we realized that there weren't no public tools available. So if you want to hack a LoRaWAN network, or if you want to audit the security of a LoRaWAN network, then you don't have any tools available. You have to create your own. You have to start from scratch. So we decided that it was a good idea to create our own tools and then share those tools. And this is important because, for instance, if you are running a LoRaWAN network, you don't really know if someone is trying to hack your network, if someone is already hacking your network, if your keys are weak. So basically, you run your infrastructure blindly, and you don't know the current status of the security. So tools also will be very valuable if they can help you to test the network, also monitor the network for cyber attacks. So right now, if you are running, everyone in Europe, in Asia, in America, that is running LoRaWAN infrastructure, they don't really know what's going on in their network in matters of security. They are just completely blind. They blindly trust the network. So we created this framework, we call it LoRaWAN Auditing Framework, which is a set of open source tools. From one side, we have the pen test tool that allow you to capture traffic, to sniff traffic over the air. It allows you to create packets also, craft packets, do some key cracking, even fuzzing of the protocol. And from other side, for the pen test tool will be for the offensive part, right? And then we have also for the defensive part. And for that, we have what we call LoRaWAN message collectors. That is a source of information, a source of LoRaWAN packets to feed the tools. So you can feed the tool, for instance, from the LoRaWAN network server. You can even feed the tool directly from a gateway. And you can also create your own collector, because there are many different LoRaWAN servers, and there could be different sources of information. So, or maybe you just, already capture a lot of traffic and you save it in a file or a database, and then you can also write your own collection to feed the tool from there. That's not a problem. The tools will take the information from any place. You should need to let the tools know where to get them and how to get them. So for the defensive part, we have what we call traffic analyzer. We'll take a look at all the LoRaWAN message that was already captured. They will try to detect possible attack. For instance, they will look and try to detect for showing replay attacks. They will also look for possible ABP activated devices. They will try to profile devices. All this, I forgot to mention, all this analysis is done on encrypted data. So it's data that you can, like I said, you can capture over the air with the gateway, gateway. So you don't need to care about being able to decrypt the data. You just need the encrypted data, and the tools will work with that. Another thing you can detect is that LoRaWAN network is using weak keys, like I said, because we have a key cracking tool which will analyze the information and try to guess by brute force the keys. And these tools are very good, because we have tried with some open servers on the internet, and we have found we have cracked keys used by real LoRaWAN networks. Another thing that it could detect is that duplicated session key. So we can detect if someone is sending the same information as other device, or trying to make it look that the information is coming from a real device and it's not. And also can detect how many devices or profile devices, like I said, in the network. So they are very useful tools.
So now I'm going to comment about the architecture of this framework. We can see that it's modularized like in 3 different modules. The first 2, the one from the left and the one in the center, they stand for like the defensive part of this framework, where at first we have the collectors. As Cesar mentioned, the collectors fetch packets from many different implementations of LoRaWAN, and they save these packets in a standard way into the DB. So now the analyzers are able to fetch those packets and run different analysis or brute forcing analysis, for example, to look for certain patterns on the traffic, and then they based on these patterns, they raise different alerts. And the last module is it's composed, or it stands for the offensive part of this framework, and it's composed by many micro tools which are meant to mainly pen test or to audit or to inject packets into a real LoRaWAN network. So we can craft messages, we can parse messages, we can fast data and send it to a valid gateway, for example, and many other things. These tools were written in Python. Maybe the 90% of the tools were written in Python 3, and the 10%, the rest, it was written in Golang. We also used SQL Alchemy for the access to the database, so that users can choose between, for example, SQLite or PostgreSQL, depending on what do you want to really do with the framework. If you want to use it for the defensive part, you may want to use PostgreSQL, or if you want to use it for defensive part, you may want to use SQLite. And all these framework is packed into a container so that users can really set up and run these tools without having to deal with the dependencies and all that stuff. So about the hardware that we were using and we are currently using, we have been talking about the gateways, the antennas that communicate with the devices. So this is a gateway. This is a semi-professional gateway. So this is composed by a Raspberry Pi 3 and a small transceiver, which is the part that can really talk in LoRa language. This transceiver, it costs more or less $200. And here it runs like 2 different components of software. And we modified one of them, which is the packet forwarder, so that the gateway can behave as if it were a device. And what's this for? This is for injecting like real packets to a real other gateways, so that we can send packets from this gateway to another gateway as if it were a device. And this is also uploaded in GitHub, so you can download and install in your gateway. By using this gateway, we found a couple of limitations. The first one is that we can only listen to uplink traffic. We try to modify the software in order to listen to the downlink traffic. I mean the one that comes from the network server to the devices, but we were not able to do this. And the other drawback is that at least with this gateway, we can only listen 8 out of 64 channels. Although nowadays we have like more professional gateways that allow you to listen the whole amount of channels, but it costs like 10 more times than this one. So having these limitations in mind, we started to think about like what to use to avoid this problem, and we came up with the idea of using an SDR. For those who don't know what's an SDR, it's like a small device you plug into your computer, and it provides you like an interface between your computer and the RF world. And then we started to research about SDRs. We found that the best one or the most suitable for this scenario was the Lime SDR, because it provides like or is the one that has the biggest bandwidth in the market, and at least is the bandwidth that we need for the LoRaWAN frequency plan that we are using, for example, in Argentina. And this device costs like approximately like $300. And we've also found that there are many plugins for LoRaWAN for the SDR software that you can download and install and set up, so that this way we can listen to both uplink and downlink traffic, and we can also we would also inject packets into the real LoRaWAN infrastructure. And now we are researching, we are trying to set all the stuff together, all the software together to make it work. And we are currently doing that. So I'm going to show a little bit about the software, the framework. I don't see the console here. Let's see. Okay. Good. So in my computer, I have a small data set that that we have collected in the office. The data set it was from a real network where we stole the app key and like generated the session keys, and then we started to inject different packets in order to like as if it were a real attack. So I'm going to launch the analyzer, for example, that's for the defensive part. And okay, we'll see that now it starts to process it's in verbose mode now, that it will process all the packets, and it allows you to process in real time as well. And let's see, for example, a couple of alerts that it fired. So here, for example, we have the alert that it found a repeated dev nodes, for example, which should be random. And here we can infer that someone maybe was trying to inject a SHA request into our network, and it says, okay, this is the ID of the message, so go and see to the database, for example. And it also tells you for which device the SHA replace was done. Another alert, for example, here it detected that it came a message with a lower counter than the last counter of the device. So here, for example, you can infer that maybe someone stole your app key and generated the session keys, and now is injecting or trying to inject real data as if it were the real device. And the last one I want to show you is, because we are also recording the location of the gateway, and for example, here it says that the gateway was moved. You can set up as if it were like a policy, how many meters do you want to check, or you want to allow the gateway to move, although it's not a common situation to have a portable gateway, but we are also checking that. So here in this situation, for example, you can infer that someone stole your gateway and he's with your gateway visiting around. So another module of the analyzer is a brute forcer, which grab SHA requests and SHA accepts and try to brute force with possible app keys that in the framework, for example, we have published on GitHub like a list of all the app keys that we have found from vendor sites, and as Cesar was talking about. So we try with all those keys, and we also generate like 2,100 more keys on the fly dynamically. So for example, here it says that this key was found for this device, which has now this device address, and using the SHA request with ID 6 and the SHA accept with ID 7. And let's check it into the database, for example. So here we have the ID 6. So here we have the SHA request. Usually LoRaWAN uses base 64 for packing its messages. So now we have this SHA request and SHA accept. And the app key, we can now derive the session keys. So I'm going to show you how easy it is to do that. I have another console here. So here we have all the input that this micro tool needs. So we are going to pass now the request. So the accept. And finally, we need the key that was found in here. And now the tools gave us the session keys. And from this part, we can start to inject packets with a valid cryptography as if we were a valid attacker. So now I'm going to go over the step that I went through. So I first had a data set in my database, and then I launched the traffic analyzers. We look for patterns in the traffic, and then I launch the brute forcer. There you have, for example, the commands I used. Then we copy the shown request, the shown accept, and the app key to finally derive the session keys. And from here to now, we can start to inject packets with a valid crypto as if we are spoofing the device.
Attack scenarios, some possible attack scenarios in real LoRaWAN implementations. So one of the use of LoRaWAN devices is, for instance, in a factory or in a home, in different places, to be able to detect fire, to measure temperature, pressure. You can have different kind of sensors, and that information is sent to the LoRaWAN network, and the applications will use that information to take decisions or, to alert people, etc. Even you can use LoRaWAN devices to put the movement detector in your house as an alarm if there is an intruder, etc. But what happens is someone hacks devices that are used to detect fire. That means that the person could, put the place on fire on purpose and disable the device, or they could, you be using sensors to detect the pressure of some pipes or the temperature of some other factory place. So if someone hacked the network, we'll be able to manipulate the values of the sense of the pressure, temperature, and that could end up putting human life at risk. That's some probably scenario when LoRaWAN technology is being used or could be used. Another scenario is about smart metering. There is a lot of push to start using LoRaWAN technology for smart metering. That means utilities having thousands of customers will deploy thousands of devices for reading the gas consumption, water consumption, even electricity. That means that if someone hacked your LoRaWAN network, then you as an utility company won't be able to charge your customers about their consumption. And that could create a lot of problems. Also, if you are, as an attacker, are able to compromise a LoRaWAN network, like we already mentioned, you can cause a denial of service and bring down the whole network, or some devices at least. So what are the possible solutions for all this mess right now with LoRaWAN? So one is important is protecting the keys, because the keys are the ones that are used to encrypt the traffic, to sign the messages, etc. So if keys are compromised, like I said, game over. You don't have any more security on your LoRaWAN network. So right now, the most secure way to protect the keys are using secure element on the devices, on the end devices, and HSM hardware security modules on the network server level or the joint server. In this way, you really protect the keys so no one can access them. There still are some threats, but you really load the attack surface. Something you have to do if you are going to implement LoRaWAN is to always change the keys that are provided by the vendors. You always have to generate new keys. And of course, use different keys for different devices. Because like we said, a common problem is use the same key for all devices, and that makes attacks a lot easier. Something is important is to constantly audit the keys your network are using. How to audit it? By trying to brute force the keys, because if not, then you don't really know what keys are using your infrastructure sometimes, or maybe your infrastructure depends on a service provider, and you as a user and the one that is the owner of the solution, the one that is using the data from the sensors, you don't really know how secure is the implementation. So as a user, I would suggest that you try to enforce security in some way, asking the service provider, okay, are you using secure keys? You don't really know. So one way could be try to crack them, to audit them and see if they are weak or not. Another thing is that you right now, in any modern TCP/IP network, you will have firewalls, you will have ADS, IPS, different kind of security software that is being used to prevent attack, to detect attack, and to react after an attack too. But right now, for LoRaWAN networks, you don't have anything. You just need to trust the security. You need to trust the service provider. So you are completely blind. So you really need tools to monitor the traffic, to detect possible attacks in real time. For that, you need tools. But also what you need to do is to audit your LoRaWAN network the same way you audit your TCP/IP network, because you need to make sure that your LoRaWAN network is secure and will be able to reject attacks. It won't be very easy to hack. And for that, okay, you have to have, your own team doing the audit, or you can hire external teams. And like I said, you need software to monitor in real time and to detect and to prevent attacks. So that's all. There is the GitHub where you can get the tools, the framework. So feel free to play with them. So if you have any question, let us know. We are really glad to have people using the tools, to contribute to them if they want, or we can help to solve problems if you have some problems. That's it. Thank you.
Thank you, Matthias and Cesar. Are there any questions from the audience? If there are not, we'll go straight through to the Slido.
Okay, the first one, will LAF work with the standard SDR radios? I don't know what do you mean with the standard SDR, maybe the HackRF or something like that? I don't know if...
It depends on the frequency of the...
Yeah, the thing is that this framework is not coupled to a certain SDR. We proposed the Lime SDR because we saw that the bandwidth, it's big enough to cover at least the bandwidth that we need there in Argentina. Although there are others frequency plan that don't need such a big bandwidth, and you can use, for example, a HackRF. There are many plugins. For example, the plugins that I showed, it works for HackRF, and it doesn't work. I mean, it doesn't support directly Lime SDR. So that that's what we were like trying to work out.
So the other question is, what kind of support does LoRaWAN need for the industry? So what kind of support does LoRaWAN need from the industry for widespread adaptation of it? What means by adaptation? Adoption or adaptation? Adaptation? Okay. Not sure what it means. Maybe it's adoption or adapted to what? No.
Yeah, because LoRaWAN allows you to build whatever you want on top of it. I mean, your application, LoRaWAN only allows you to send messages to devices that are remotely, so that you can put whatever you want on top of LoRaWAN. And there is, in my opinion, I think that there is already a lot of support from the industry to make things work. And there is, as Cesar mentioned, there is a lot of LoRaWAN being deployed all over the world.
Okay, the last question is it common for the LoRa devices to be configured via Bluetooth? Is it rather classic Bluetooth, VR, EDR, or the new low energy that often does not require pairing, just some app layer pass? Yeah, I don't remember what kind of Bluetooth was being used, but
it was BLE. I mean, the first question, it is not common or not most of the devices are configured by Bluetooth, but the other day you sent us, for example, a user guide that it had a device with BLE, for example.
Yeah, and the default password was in the documentation. So it's not all the devices are configured by a mobile app by Bluetooth, but some of them, yes. Yes, there was a Bluetooth low energy. I'm not sure about the other version of Bluetooth. But yes, you have the password sometimes is 11111, so you can brute force, or sometimes on the documentation, the default password. So, the common problems related with Bluetooth. So basically it's a threat to have a device with Bluetooth enabled for configuration. Yes, yeah.
How do you find those price points better, not better?
Well, the main
3 years' time, how do you
one of the main difference people mention about that is that LoRaWAN, while the LoRa part is patented by Semtech. So Semtech is the owner of LoRa, the radio frequency part. The other part are all open source, all open. But Sigfox is complete proprietary, everything. So if you want to use Sigfox, then you have to work with that company, with their services, with their ideas, with everything. So you are tied to them, and it's a proprietary technology. But in case of LoRaWAN, you can put your own LoRaWAN server, your own infrastructure. You can do whatever you want.
And there is a lot of open source software.
Right.
If you want to, for example, set up a network server, you have like at least 3 or 4 different open source solutions that are pretty much well developed.
I think, yeah, the main difference, I would say that one is open, maybe not completely, but it's open, and the other is closed. It's a proprietary, and you depend on just one vendor.
So going by traditional trends, open source should take the market share.
Yeah, I don't know. They are heavily competing right now. Sigfox has developed many partnerships with telecommunication providers. They are, covering a lot of the world with Sigfox technology. So they are competing head by head. I'm not sure who will win, if both will stay over time. But right now, for us, LoRaWAN looks more promising.
The cloud for LoRaWAN, it is available in the cloud basis or on-premise?
Yeah, you can have both. So service providers, like I said, you can have your own infrastructure. You can own everything from the LoRaWAN network infrastructure, or you can use third parties. So for the third parties, they will provide on cloud services, and they will also provide on-premises services, depending on your needs.
Yeah, and they will provide, for example, their own gateways and their own network servers or joint servers. There are many countries that are all covered by LoRaWAN gateways, for example. So you just have to pay monthly. And
okay, when I start installing this firmware, I need only one agent.
Sorry?
Just to do this scanning, I need only one agent.
For the tools,
Yeah.
you can collect the information you can get the information from many sources. One source is using the gateway, using a gateway. You can capture all the traffic over there, just listening in the appropriate channels, and you get that traffic and feed the tools. Another way is there are many open servers on the internet, MQTT servers, where the information is being set by the network server. So you can take the information from MQTT servers and feed the tools, or you can have the information in a database like he showed, and feed the tool from the database. So basically the tool will take information from anywhere. You have...
For defensive part, I recommend to grab the messages from the MQTT servers that are fed by the network server. And that's there you have like more rich information than in the gateway. Yeah. And that way you should only collect in one place, and that's it. You
in
grab
one site only. It is not required to like.
There's only one.
Yeah, and also for the defensive, probably you are the owner of the infrastructure. You have access, so you can choose that part. that way, which is the easiest part. But for the offensive, if you are testing the LoRaWAN network or if you are trying to hack it, then you probably will go with a gateway and try to
or an SDR maybe in the future.
Okay, thank you.
Thank you.
Thanks.
Any more questions?
Okay.
Then I would like to thank you.
Thanks.
I would like to thank Matthias and Cesar. Thank you.
Okay. Thanks.
Give him a big applause.